In the vast darkness beyond the familiar orbits of our solar system, a silent visitor is making its way through, born in a distant stellar nursery, cast into the void, drifting for millions or billions of years. This traveler is 3I/Atlas, an interstellar comet, the third ever confirmed to cross into our solar system. It carries with it the echoes of another time, another place, a fragment of cosmic history we've only begun to glimpse. When we detect something like 3I/Atlas, we are peering across unimaginable distance. We are touching, through telescopes and detectors, material formed in environments wholly alien. Its arrival is rare, its path is fleeting, and its revelations are profound. 3I/Atlas was first observed by the Atlas Survey Telescope in Chile on July 1, 2025, though telescopes earlier had caught glimpses in archival images, extending the observation arc to mid-June. What defines it as interstellar is its hyperbolic trajectory. The comet is not gravitationally bound to the Sun. It's coming from outside, sweeping through, and soon to depart, never to return. Its speed relative to the Sun is extraordinary. Observations show an inbound velocity that far exceeds what ordinary solar system objects display. Because of this, 3I/Atlas offers a once-in-a-generation chance to analyze matter unprocessed by our Sun's birth, to sample materials formed under different cosmic conditions, and to compare them with our own comets and asteroids. Early observations constrain the size of 3I/Atlas's nucleus to somewhere between 440 meters and 5.6 kilometers in diameter. This uncertain range is wide because it depends on how much dust and gas is surrounding it, the coma, how bright it appears from Earth, how fast it's outgassing, and how much sunlight it absorbs and reflects. But even at the lower end, it is substantial. If near the upper limits, it would indeed make it one of the largest interstellar comets yet discovered. The comet is clearly active. It exhibits a coma of dust and gas, a tail, and increasingly strong signals from volatile compounds like carbon dioxide, CO2, water, H2O, and possibly others. Observations from instruments, including the James Webb Space Telescope, JWST, reveal a CO2-dominated coma, meaning CO2 emission is much stronger compared to water, more than is typical for many known comets. Also notable is that it displays OH emission, a proxy for water activity, at distances beyond where water ice sublimation is usually efficient. That tells us that this comet is active even far from the Sun, indicative of significant volatile material and possibly large, icy grains in its coma which release water vapor. The spectral data gathered so far paints a picture of 3I/Atlas as atypical in some respects. Its CO2/H2O mixing ratio is very high, among the highest yet observed in a comet, suggesting either that the nucleus has a composition unusually rich in CO2, or that its internal structure and thermal properties suppress water outgassing relative to CO2. Aside from CO2 and H2O, detections include dust, water ice grains, carbon monoxide, CO, and some trace species. Also, astronomers have detected cyanide emission in its coma. Such molecules are common in comets, but the ratios and behavior, how and when they're released, seem different. Part of what makes 3I/Atlas special is not just that it has these things, but how strong some emissions are relative to others, especially at large distances from the Sun. Another oddity, polarimetric observations, studying how light is polarized by the dust and particles, show that 3I/Atlas has a deep and narrow negative polarization branch and an inversion angle that are unusual even when compared with other comets and asteroids. These measurements suggest that the dust grains in its coma may be large, complex, possibly aged or processed in ways different from typical solar system comets. 3I/Atlas will approach closest to the Sun, perihelion, around October 29, 2025, at a distance of about 1.36 astronomical units, AU, placing it just inside Mars's orbital distance from the Sun. Its closest approach to Earth will still be relatively distant, about $1.80, roughly 270 million kilometers / 170 million miles. That distance means it poses no threat to Earth, but it does mean it will be observable mainly with powerful ground-based telescopes and space observatories, not with the naked eye. Observations are expected to be possible through September 2025, after which the comet will move into a region too close to the Sun from Earth's perspective, solar conjunction, making it difficult to view. Then it will re-emerge on the other side toward the end of the year. NASA science. One of the most important aspects of 3I/Atlas is that its properties may push us to rethink our models. Volatile inventory in interstellar objects. The strong CO2 dominance suggests that some comets in other stellar systems may retain or form with higher proportions of CO2 or other volatiles than many comets in our own solar system. This raises questions about how and where different comets form in their home systems. For example, near or beyond different ice lines, regions where certain ices can condense. Age and origin. Some analysis suggests that 3I/Atlas may be very old, potentially forming in a low metallicity environment, perhaps in the thick disk of the Milky Way, which would mean it has survived for many billions of years in interstellar space. If so, its current composition, surface properties, and dust might reflect a history of radiation exposure and volatile loss. Dust grain properties and behavior. The unusual polarization and coma/dust behavior indicate that the dust grains may be relatively large, possibly less processed, or with different optical properties compared to typical solar system comets. That gives clues about how dust evolves in interstellar environments, how aging and space weathering occur, and how comets behave far from the Sun. Outgassing behavior at large solar distances. That 3I/Atlas shows water, via OH emission, and other volatile activity at heliocentric distances beyond where water sublimation is usually efficient is surprising. It suggests mechanisms, e.g. icy grains, subsurface heat, or very volatile molecules, sustaining activity far from the Sun. Another window into how comets from cold outer parts of stellar systems behave. When we see an interstellar object like 3I/Atlas, we are reminded how small we are, but also how connected. It is material from another star passing through our space, temporarily illuminated by our Sun, briefly seen by instruments we have built. It invites wondering, what kind of solar system did it come from? How many cycles of planetary formation, collisions, and migrations has it survived? What does its composition say about the building blocks available in its home neighborhood, perhaps different from ours? It also reminds us that the Milky Way is not empty. It's full of ancient rocks, wandering debris, cosmic flotsam, and maybe even things we haven't conceived yet. Every interstellar visitor is a messenger, not of life necessarily, but of formation, of history, of diversity. Soon, 3I/Atlas will pass close to the Sun, brighten, then recede into the void it came from. It will leave the solar system forever, unless some future instrument or mission has followed it. Though we may never send a probe in time to intercept it, it has already given us something precious, Data, spectral signatures, dust samples, from afar, morphology, chemistry. It has expanded our understanding of what comets can tell us about the universe. 3i/Atlas reminds us that sometimes the universe isn't just something to observe. Sometimes it reaches across the void and gives us something unexpected, a chance to learn, a chance to wonder, a chance to see beyond our solar system from our solar system. And though the comet is a silent traveler, its passing echoes loudly. In telescopes, in spectra, in the shared human desire to know what lies beyond. Let this comet be a harbinger not of danger, but of discovery.